All right, guys, so now that we have learned about a lot of different types of organic compounds, we're going to talk a little bit about how they interact with each other. That's going to be our focus this week. So I'm going to go through this set of slides about intermolecular forces. So hopefully this isn't a surprise to you that different substances have different properties. Okay, and here's some examples of what I mean by that. Water takes a long time to dry. If you get your hands wet with water and you don't dry them off, it will take them a while to dry on their own. Whereas alcohol, like what you find in hand sanitizer, it dries so fast that it makes your hands cold. Okay, that's a difference in properties between water and alcohol. Similarly, if you look through your cupboard, a lot of us have coconut oil in our cupboard, and then we'll probably have some other sort of vegetable oil, maybe canola or something. And you'll notice that most coconut oil, unless it's been processed in some way, is solid when it sits in the cupboard, whereas vegetable oil is a liquid. Difference in properties. And then one more, this one uses some numbers to describe it. So water, we all know, freezes at 0 degrees Celsius. But carbon dioxide doesn't freeze until you get down to almost negative 80 degrees Celsius. Okay, so again, a difference in properties because of a difference in freezing point. So these different properties, particularly physical properties, depend on intermolecular forces. Okay, I know that's a huge mouthful. You'll see me refer to them as just IMFs throughout this. Okay, and basically what intermolecular forces mean is that if you have two molecules near each other, they might be able to stick to each other pretty well. You're kind of seeing these two molecules stick to each other as they interact. Okay, and the stronger the intermolecular forces, the stickier the molecules will be with each other. Now, molecules that have strong intermolecular forces are more likely to be a solid or maybe a liquid at room temperature. They'll have higher melting and boiling points, and they'll take longer to evaporate. Okay, and then you can also think this through in terms of like if I had changed this word to weak intermolecular forces would mean that things are more likely to be a gas at room temperature. They have lower melting and boiling points, and they evaporate really quickly. Okay, so strong, these three, and then the opposite would be true if the intermolecular forces were weak. So I've got a little activity here. You might want to pause the video and think it through, or you can just watch me talk about it. So we've got 5 different pairs of substances that you probably have encountered in your everyday life. And I want you to, based on this idea of how intermolecular forces lead to these different properties, see if you can guess which substance has the stronger intermolecular forces in each pair. So if you want to pause the video and think it through right now, go ahead and do that. I'm going to continue on though. So between the two substances, water and carbon dioxide, I know that water has the stronger intermolecular forces, and the easiest way for me to explain that is that water is a liquid at room temperature. I can pour it out of the tap, whereas carbon dioxide is a gas. Okay, so that tells me that water has stronger intermolecular forces. Then between alcohol and water, the way I would explain this kind of goes back to the hand sanitizer example I gave earlier. Hand sanitizer, which is made mostly of alcohol, evaporates really fast, which tells me that its intermolecular forces are weak. So then water has the stronger intermolecular forces. Okay, next pair is sugar and salt. These are two white solids that you find in your kitchen. And they might seem like they have very similar properties at first, but one thing that you may have noticed if you're into cooking is that sugar will melt on the stove, but our stoves in our kitchens will never get hot enough to melt salt. Okay, and that's because salt has incredibly strong intermolecular forces. Okay, so sugar will melt on our stove, whereas salt never will. Next pairing here, we've got olive oil and butter right there. Okay, so you can probably imagine that butter has the stronger intermolecular forces. If you have some olive oil and you leave it out on the counter, it will be a liquid, whereas butter, will be a solid. It might be a soft solid. Butter does soften at room temperature, but it's still more solid than olive oil, so it has stronger intermolecular forces. And then my last pairing here, we've got propane, which if you have a gas barbecue that has those like big tanks, that is the fuel that runs the barbecue. And then octane is a main component in gasoline. Okay, so between those two, propane, if you've ever been the person who had to turn on the barbecue, you'll know that it's a gas. Whereas if you've ever pumped gas into your car before, you know that it's a liquid, which tells me that octane is the one that has the stronger intermolecular forces. Okay. So, what causes intermolecular forces? There's kind of two things at play here. One of them is just the combination of atoms that make up the molecule. Certain combos of atoms will help molecules stick together better. And then the other thing that dictates it is the size of the molecule. Bigger molecules have more opportunities to stick to nearby molecules, so they will have stronger intermolecular forces. So we're going to move from sort of the general to some slightly more technical stuff here. So we're going to talk about electronegativity because it plays a really important role in intermolecular forces. Okay, so electronegativity obviously has to do with electrons and the fact that they are negative. Okay, and the reason that we want to focus on this is because some atoms attract electrons more strongly than others, which means that if you have a molecule, there's all these electrons and they can kind of dance around and go wherever they want throughout the molecule. But if there's a more electronegative element, then the electrons will tend to stick around it more. Okay, and then that means that part of the molecule is going to have a more negative charge because the electrons are negative. Now, electronegativity is something we can kind of predict by looking at the periodic table. So I'm going to call up a picture of the periodic table here, and it's color-coded according to electronegativity. So you'll see that things that are greenish colored have really low electronegativity, and things that are red have higher electronegativity. Okay, and the really high electronegativity is sort of clustered in this area of the periodic table. And then the really low electronegativity on this side with all the metals. Now, because we're in the unit talking about organic chemistry, we're really going to be focusing around this part of the periodic table plus hydrogen over here, because those are kind of the elements that are involved in organic chemistry. But this is just sort of a broad picture of what it looks like. Okay, so in a bond, which is how molecules are stuck together, they have bonds. In a bond between elements with different electronegativities, the electrons will be distributed unevenly. So if we look back at that table for a second, you'll see chlorine right here is red. It's a very electronegative element, whereas hydrogen over here is kind of yellowish. It's not very electronegative. So when those two are bonded together, the chlorine, it ends up being like the more negative side of the molecule because the electrons are more attracted to the chlorine. They stick around it more. Whereas the hydrogen, because the electrons don't really care for the hydrogen, it ends up being a little bit positive. Now, when we have a difference like that, we call it a polar bond. Okay, because we say that it's like there's a pole here, kind of like a magnet has a pole. Now, kind of the opposite of that is when you have two atoms that have the same attraction to electrons, the same electronegativity. So chlorine, even though it's very electronegative, if it's making a bond with itself, no one wins the electrons. They are equally attracted to both. So we would call this a non-polar bond. There's no part of this molecule or part of this bond that's extra negative or extra positive. Okay, so the charge here, the negative, is evenly distributed. Whereas in the polar bond, the negative charge sticks to one side. Okay, now when we have these polar bonds in a molecule, it depends on the shape a little bit too, but usually that means that we have something called a dipole, which means that there's one part of the molecule that's negative and another part of the molecule that's positive. Okay, so this picture right here is showing a water molecule with a negative side and a positive side. Okay, and we say that that's a dipole. Okay, so this is just another version of the electronegativity table. It's color-coded a little bit differently, but I just wanted to emphasize how these elements right here, nitrogen, oxygen, fluorine, chlorine, they show up in our organic molecules that we've been talking about. And these are pretty electronegative, so they'll tend to cause a dipole in a molecule, okay? Whereas carbon and hydrogen are less electronegative, so they tend to, they either won't cause a dipole or they'll be the positive part of the dipole. Okay. So you might want to take a second and pause this and see if you can have a think through this. Which of these molecules will have a dipole? I'm just going to launch into it though. So if we look back here, remembering that when things have nitrogen, oxygen, fluorine, or chlorine, those are pretty electronegative and those tend to cause a dipole. So looking at ammonia right here, I've got nitrogen, so that is going to be a polar, or that is going to create a dipole in the ammonia molecule. Whereas methane right here, it only has carbon and hydrogen. They have pretty similar electronegativities. The electrons don't focus on one atom over the other, so methane doesn't have a dipole. Okay, so this one, no dipole. Chloromethane though, because of that really electronegative chlorine right there, dipole. Ethanol with an oxygen, dipole. Propene, no oxygen, no nitrogen, no chlorine or fluorine, no dipole. But then methanol right here has an oxygen, so it will have a dipole. So you can kind of see a pattern here. When things have nitrogen, oxygen, or one of the halogens, that causes a dipole. If it's just carbon and hydrogen, no dipole. Okay. So the last thing we're going to go through here, there are 3 categories of intermolecular forces. And the first 2 really relate to that dipole stuff that we were just talking about. And then the last one is related more to the size of a molecule. Okay, so we'll start with this idea of hydrogen bonding. So hydrogen bonding is the strongest type of intermolecular force that we find in organic compounds. And it happens when you have a hydrogen that's bonded to oxygen, nitrogen, or fluorine. Okay, and some classic examples of molecules, organic molecules that have hydrogen bonding are carboxylic acids or organic acids, alcohols, and amines. And this is the intermolecular force that is in water. And it's dipole and hydrogen bonding are going to look very similar. The only difference between them is that the hydrogen just makes it that much stronger of an intermolecular force. Okay? Dipole forces are the middle type strength of intermolecular force. So these are very similar to hydrogen bonding, except they don't have a hydrogen bonded to oxygen, nitrogen, or fluorine. Okay, so it's still like a pole on or a dipole on the molecule that sticks to other molecules, but it's not the hydrogen that's involved. Okay, so ketones, aldehydes, and ethers are examples of molecules that will do dipole forces. And then the last type, London dispersion forces. These are our weakest intermolecular force because they are most important for non-polar molecules, so things like hydrocarbons that don't have these negative and positive parts. And they happen because the electrons are always just kind of moving around in the molecule. So I've kind of got a picture of that. And every once in a while, the electrons will organize themselves so that those molecules want to stick together. You're kind of seeing that here. And it's most important for larger molecules. Okay, that's it for this video. Thanks so much for watching.